All right, we're live. This is Radio Booster. This is the Schumann Resonance Harmonics. Hello. This is the Schumann Resonance Harmonics channel on Facebook and YouTube. And, oh, good golly, we're taking over the galaxy with your love and support. Thank you all for being here. This is part two of the, or part B, whatever, of the, this part of this discussion on spectrograms. Okay, so there's a broader, larger discussion going on, but specifically we're trying to nail it down to the Schumann resonances and understanding that. First, let me just say thank you all for being here. This is what the hell? It's the 27th of October, 2020, I'm doing this part without the overlay of the video because, quite honestly, the video block there was getting in my way of the tabs and everything, just became for doing this. It's a pain in the neck, and plus I want to have the whole screen devoted to the lesson, what we're looking at. That's the first thing. The second thing is I actually, in the time between that one and this one, I have actually bought a copy of the capture software, so it's not automatically going to cut me off at 10 minutes as far as I know. However, I do have a timer running because I do like cutting these off at 10 minutes or thereabouts. It's just not going to do it rudely at this point. And as long as I remember to tend to the timer, I should keep it. So anywhere between 10 to 11 minutes is kind of my goal on these. So this is the first run with me actually having bought the software. So we'll see how we're doing. All right. And so what we're looking at here, just really briefly, is this is the one from, just picking up kind of where we're at. If you remember on the top of the website, the article we're reading, there's this the spectrogram of the optical light from Hubble. Okay. Now below this is the spectrogram from Tomsk. Okay. And we're trying to give everyone the idea of the parameters of what the spectrogram or the spectroscope of the observatories, plural, Hubble being an observatory, Tomsk being an observatory, blase, what the parameters of the spectrograms are, that there's a band of light, show enough, but it is at the radio frequency, and that's where the Schumann frequencies are tuned into. Okay, and so this is an important discussion to have here as we're talking about a spectrum, spectrograph, sorry, and looking at what the spectrum is. How do you read a spectrum? Light carries information about the material with which it interacts. Different materials interact differently with light, and we can use light to understand what something is made of. All matter is made of atoms. Oh, hold on. My cable has got stuck here. I dislike cables, I dislike wireless. All right, so all matter is made of atoms. Electrons go around the nucleus of an atom at different allowed energies, like rungs on a ladder. Light, with the exact energy needed to go between rungs, can be absorbed, but not others. Electrons fall down to lower rungs, emitting light at the specific energy of the difference between the rungs. This allows different atoms to emit different colors of light. Sodium spectrum does not look like nitrogen spectrum, nor like the spectrum of any other element. All elements absorb and emit specific wavelengths of light that correspond to those energy levels. An absorption spectrum is a spectrum of light transmitted through a substance showing dark lines or bands where light has been absorbed by atoms, causing a dip in the spectrum. An emission spectrum emission spectrum is made by electrons falling down the energy ladder. It's what you get when you look at hot gas, which is heated by something out of the line of sight. This heating moves the electrons up the ladder. Then when they fall down the ladder, some of the light they emit comes to you. This results in bright colored spikes due to atoms releasing light at those wavelengths. Okay, and they give you a little chart here. Bam! Look at that. All right. These are a nanometer. All right, nanometer. That's what these wavelengths are. Tiny, tiny bits of light. All right. So this scale of the visible light, I need to say, is of a finer frequency than the Schumann frequencies. Schumann is measured in radio waves, which are at the lower end of the light spectrum. Okay, it's really important to remember where we are in the scale of things. Okay, so this chart here that they're showing you is the one that was on the top graph at the beginning of this video that I had on the top. They're talking about this specifically to that spectro that they're getting there. All right, so I just want to make that kind of as a key point to note. All right. Electrons in an atom can only exist on certain energy levels. When an electron moves down from one rung of the atom's energy ladder to another, a particle of light is emitted whose energy matches the change in the electron's energy. Different elements have rungs in different places on the energy ladder. Okay, and so the same thing falls with frequencies at the radio. And you see what, oh, come on, don't do this to me here. So I can't even get in there. So one of the things I want to point out here are what they're showing you here in this little graph to the right of the cursor is also the modes. M-O-D-E-S. See, they're giving you different color there. They're arbitrarily colored there, but this is what we're talking about with the Schumann spectrogram of these modes, but of a different lower frequency of light than these here, right? Are you starting to get a picture of this? That it's a different, octave of light, if you will, than the radio frequencies, but it's the same basic principle I'm sorry, I got an itch on my face here. It's the same basic principle at work of what we're looking at. See, this would be, oh, good golly, I wish this thing wouldn't do this to me. Actually, hold on. So this right here would be your white peak. This would be your yellow. That's your red. And that's your green of the Schumann. Hopefully you're following me and I'm not going crazy on you and you're following me. So this would be the mode 1 of the amplitude. This is mode 2 of the white, A1. This is A2, which is yellow, A3, which is red, and A4, which is green. On our Schumann, we're comparing apples to oranges, but we're doing the best we can. All right, so back to the text. All right, if you follow me here, okay, so they're looking at it's the same different sort of thing here with the wavelengths and the frequencies. All right, let's expand it. Hold on. All right, so it's the same thing with these here frequencies. So this would be, if this is in the magnetic band, it's going horizontal this way, for example. We have, this is our green mode. Forget which way we're going. I think that would, if this is our magnetic, I think this would be the Q1, Q2, Q3, and Q4. I think. I'm not sure. Don't hold me to that. Okay, but I'm just making a comparison here. All right. So this diagram illustrates how Hubble Space Telescope spectral observations were used to study the chemical makeup of the Southern Crab Nebula. Hubble Space Telescope Imaging Spectrograph, STIS, divided the light from the nebula's filaments to record the emissions from hydrogen, sulfur, oxygen, nitrogen. They're going to the most basic to more complex. So nitrogen is a 1, sulfur, I forget what that number is, but oxygen is 8, and nitrogen is 12, I think. I forget what their atomic numbers are, but you get the point. I know oxygen's 8, and that's 1. Helium is 2. Sulfur is, I don't know, 4, 5 maybe. All right. I forget what sulfur is. Anyway, the combinations of STIS spectroscopy and the image of Hubble's Wide Field Camera 3 shows specifically which gases were detected and how they were distributed in the nebula. All right. So this is sort of what, you have the if you can, picture an electromagnetic frequency for those as well, you're starting to get the image. All right. How does a spectrograph work? A spectrograph passes light coming into the telescope through and in our case, it's not a telescope, it's coming in through the antenna, okay? Through the Schumann antenna. I think I've shown a picture of that. I certainly have, and we'll get into some other point again. A telescope through a tiny hole or a slit in a metal plate to isolate light from a single object or area. This light is bounced off of a special grating which splits the light into its different wavelengths, just like a prism makes rainbows. The split light lands on a detector which records the spectrum that is formed. Okay, all right. So you can see what it's doing. The spectrum, and these are a relative Schumann, again, they're breaking this up into these colors here, the spectrum of the light, but this is not Schumann resonances here, okay? Even though you're seeing, light, and this is light, this is optical, this is a higher frequency than the radio waves of Schumann, okay? So just, again, as a kind of disclaimer, all right. What has Hubble found with spectroscopy? Hubble's spectrographs reveals important details of many aspects of our universe. Below are examples of the many spectroscopic findings from Hubble. Okay, and then we have recording a black hole signature, uncovering gas swirling at hundreds of miles per second around a black hole at the center of another galaxy, providing first direct detection of the atmosphere of a planet orbiting a star outside of our solar system, detecting an organic molecule in the atmosphere of a planet orbiting another star, finding what were thought to be randomly distributed nearby primordial clouds of hydrogen may actually be associated with galaxies or clusters of galaxies, showing, this also got some part B here, I'm well over 10 minutes, showing the massive clouds of ionized gas are raining down from our galaxy's halo and intergalactic space and will continue to provide fuel for the Milky Way to keep forming stars. Fingerprinting the distant universe using the light from a quasar, allowing astronomers to probe the raw materials from which galaxies form and determine how this gas was assembled into complex structures of the present-day universe. All right, last updated, this is from May 30th, 2019. All right, okay, all right. So you get the basic picture here of what's going on. I'm, over the time limit that I had set, hopefully not for you uncomfortably so. With that, on that cheery note, I get to gracefully, peacefully exit without being rudely shut off. Thank you all for being here. You are all wonderful. And just because you are all wonderful, you've held on this long. Let's see what's in the recent files. Oh, this one. All right, I'm going to take us out with some music because you've been so wonderful. And we have a different scope here.
break, stop looking, let's go out of sight.